Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 30 of Algebraic Topology. In previous lecture, we studied some cellular homology, and then we studied homology with coefficients, and then we started a new topic called the covering spaces. In this lecture, we will continue our discussion of the covering spaces, and we will explore some properties of covering spaces, including their relation with the fundamental group. So let's begin with today's lecture. So let us recall ourselves what is a covering space. So a covering space of a space X is X tilde together with a continuous function satisfying the following condition. So we want X tilde to be path connected, and for each X belongs to capital X, there exists an open neighborhood U such that P inverse U is disjoint union of open sets such that P restricted to UI from UI to U is a homeomorphism. Okay, so basically there are many other things which are hidden inside the definition. So for example, when it says that P inverse U is disjoint union of open sets, so it means that if I take a point X, then the inverse image, okay, so let's say there exists an open set containing this small x, then the inverse image of this U is basically disjoint union of open sets in here. So in other words, we can say that inverse image of X is going to be a discrete set, because the inverse image of X will be contained in disjoint union of open sets. So in other words, we can say that this is going to be a discrete set. In other words, we should be able to list down the P inverse X elements in the following way. So X1, X2, X0 up to so on. Okay, so that's what it means by a discrete set. And similarly, we can also see that the inverse image of U is going to be collection of open sets, and every open set, so let's call it U2, let's call it U1, let's call it U0. So this U2 is homeomorphic to this open set U, U1 is homeomorphic to U, U0 is homeomorphic to U. So in other words, we can say that if I consider the inverse image of this X, then it's going to be, let's say, X0, so this X0, X1, X2, so X0 contained in U0, X1 contained in U1, X2 contained in U2. So this neighborhood, so locally around X, this space is homeomorphic. So when we say homeomorphic, it means topologically there is no difference. So this open set U0 around X0 is homeomorphic to this open set U around X. So locally they are homeomorphic. So in other words, we can say that the covering space locally it's homeomorphic to this base space. So and we denote this covering space by X tilde P, because both of these things are important. We need a covering space and we need a continuous function, which is called projection map. Okay, and this space X is sometimes called the base space. So let us begin by considering a very interesting example of the covering spaces. Okay, so this is this S1 wedge S1. So what is this space? So we have studied this thing when we were discussed this wedge sum. So basically take two circles with 1 point on each circle labeled. Okay, so let's call it X0 and let's call it X1. So this is S1, this is S1. Now take their special product and the quotient in a way that this X0 is identified with X1. So in other words, just take two circles and identify and choose 1 point on each circle, and then identify those 2 points, and then we will get this wedge S1. Now the covering space of S1 wedge S1 represent most of the theory of covering spaces very precisely. So in other words, if we considering the covering spaces, of course when I'm saying covering spaces, it means that we are going to consider more than one covering spaces of the space. So they represent most of the theory. So if we consider these covering spaces very thoroughly and very precisely, then we will be exploring some very important ideas of this theory of covering spaces. So let us start by looking at some of the covering spaces of this space. So let us fix some things before we start. So let's call S1 wedge S1 X, so that we don't have to write this again and again. So the space X can be considered as a graph with one vertex X. Okay, so what is a graph? A graph is a collection of edges and vertices. Okay, yeah, so for example, this is a graph with 3 edges and 3 vertices. Okay, so in this case we can say that it is a graph with one vertex X and 2 edges, and these edges are oriented. Okay, so in this particular case the edges of the graph are not oriented, so we can consider a graph with oriented edges as well. Okay, so similarly we can consider other graphs. So similarly this is also a graph, and if we orient its edge, the only edge, then it will be an oriented graph. Okay, so it is a graph with one vertex X and 2 edges A and B, and we can see the orientation of A and B. Okay, also we know from our previous discussion that the fundamental group of S1 wedge S1 is Z star Z, and it is generated by A and B. Okay, so it is basically the free product of Z and Z. Now a trivial covering of X is given by just taking 2 copies of this wedge sum X. But there is a problem here, because this space doesn't seem to be path connected, and we want our space to be path connected. So what should we do? So we can join these 2 copies of X together in some way. Okay, so let's see how we can do that. So I can cut this space from here and cut this space from here, and then I can join this edge with this edge. Okay, so this is basically one edge, and I can join this edge with this edge. Okay, so basically coming like this and then going to like this. Okay, so something like that, and there are arrows like this. Okay, so in other words, what I'm trying to say is consider space like this. Okay, so there are 2 circles which are not cut down, and then there are 2 circles which are cut down and join in this way. Okay, so this is the space that we get after cutting and joining these 2 circles. So we can see that this space seems like path connected now, and this forms a covering space. Now I can write down this space in a more clever way, and this is the way. Okay, so basically I can open up this space, and it will become something like this in flat form. Okay, so let's explore further properties of the covering spaces. Okay, so why it is a covering space? So one thing is very clear, that if I take any point on the space X, then the inverse image of this is going to be, so let's call it X, and the inverse image is going to be this point X1 and this point X2. So why is that? Because when we move along A, then basically in our covering space we are moving along this A, so that's fine. Okay, and then when we move to B, Okay, so when we move along B, this whole B, then basically we are moving along this B. Okay, so that's one cover of this space. So now if I move again along this A, then I'll be moving along this A. And when I will be moving along this B, then I'll be moving along this B in the covering space. So that's why if I take this point X in this space capital X, then the inverse image of this is going to be 2 points. So one of them is X1, because this is the first A that this is the first part which is in the covering space above this loop A. Okay, so what is the second part which is in the covering space above A? So it is this A. So it's more clear in this diagram that this is the A part, and there are two circles above this A, and this is the B part, and each part of this basically covers. So it's just like you take a circle, and there is an helix above it. Okay, so that you cover this circle. Okay, so this whole thing is covered by this helical portion. Okay, and similarly once again then you go to this A, and then you come back, then once again the second part is basically the second portion of the helix. Okay, so that's how we cover the space X. Okay, so now take this point X and take this open set around this set, then the inverse image inside this P. Okay, so this is our projection map. So the inverse is going to be this U1 and this U2. Okay, and of course we can see that they are homeomorphic. Okay, but the problem arises when we are at X. So let's explore if this property is satisfied when we try to take an open set around X and try to discover that whether the inverse image of that open set is homeomorphic to this set or not. Now let's see what happens at point X. So if there exists an open set around this X, let's call it U prime, then the inverse image of this open set is going to be this portion and this portion. So once again, if you are not convinced, then you can have a look at this diagram. So the inverse image of this is going to be this set and this set. Okay, so let's call this point y1, and let's call this point y2. So the inverse image of this point X, and basically this is X prime, so this is X, so the inverse image of X is basically y1 and y2, and let's see if these this set U prime is homeomorphic to this set. Let's call it y1 prime and y2 prime. Okay, so at point X, so there is one edge of A going out, one edge of A coming in, and one edge of B coming going out, and one edge of B coming in. So the same happens at point y1. So one edge of A going out, one edge of A coming in, one edge of B coming out, and one edge of B coming in. Okay, and similarly we can say the same, we can see that the same things happens at this node y2. So one edge of B coming in, one edge of B coming out, one edge of A coming out, one edge of B, one edge of A coming in. Okay, so in other words we can say that these this U prime is homeomorphic to this y1 prime and this y2 prime. So all the properties of the covering space are satisfied. So this is one covering space of capital X. Now let's consider another covering space of our space X. Now consider this space. Now if I point X here, which is the central point, the only vertex in this graph, then the inverse image of this is this y1 prime and y2 prime. Okay, now if I take any other point, so let's call it T, then the inverse image of T is going to be 2 points. Okay, so you can see that when we start traveling along A, then this T is you can say that 1, 2, 3, 3/4 of the way of A. So in other words, we can say that the inverse image of this is going to be, so this is first A and this is the second A, so it will be 1, 2, 3, so it will be somewhere over there. So let's call it T1, and along this A it's going to be 1, 2, 3, so somewhere over there, so T2. Okay, so these are the inverse images. Okay, so P inverse of T is going to be equal to T1 and T2. Okay, so if I take an open set around T, then it will give me open sets around this T1 and T2, and we can see that they are homeomorphic to each other. And if I take an open set around this point X, then I will get 2 open sets around Y1 prime and Y2 prime. Let's call them U1 and U2, and let's call this open set U. So the inverse image of U is U1, U2, and U1 and U2 both are homeomorphic to this this open set U, because once again we can see that there is one edge of A going out, one edge of A coming in, one edge of B going out, one edge of B coming in, and same is the case in U1. So one edge of A coming in, one edge of A going out, one edge of B coming in, one edge of B going out, and similarly for the case U2. Okay, so we can see that all the properties of the covering space are satisfied. So that's another covering space of the space X. So there are some other examples of the covering spaces which are given below. Okay, so once again this is the covering space, and we can see that at each and every node the same property happens, and if I take any intermediate point other than the node, then of course it will be homeomorphic, and same is the case in this case, same is the case in these two cases. For more details you can see the book of Alan Hatcher. There are some other covering spaces in that book as well. So let's consider another covering space. So now instead of taking a closed thing, now we are basically taking an infinite string. And what is this string? So first we start with B, and then we have a loop of A, and then we go along B again, and then we have a loop of A again, and then B, and then loop of A, and this is an infinite string. Okay, so what will be the inverse image of this point X? So the inverse image of this point is going to be this point. So let's see if the property is satisfied. So one edge of A going out, one edge of A coming in, one edge of B coming in, one edge of B going out, and same is the case with the other inverse images. So for example, if this is U, then this is U1, U2, U3, and all of these UIs are homeomorphic to this open set U around X. And similarly, if I have some other point T and there is an open set, let's call it Y, then this T will be along somewhere over there, and this is going to be an open set, so let's call it Y1, and the inverse image of this T is going to be infinite set with infinitely many open sets, so Y2, Y3, up to so on, and each and every open set is homeomorphic to this open set Y. Now there is an important observation about all of these covering spaces of the space X, and that observation is that we can find loops in that spaces. Okay, so for example, in this space I can find loops. Okay, so this is one loop, this is another loop, and then in fact I can go around and I can take another round along A, and this will be another loop. Okay, and similarly I can find loops corresponding to this portion of this covering space. and up to so on. So let's go back. Does this hold for the previously discussed covering spaces as well? So let's see. Of course this is true. We can easily find loops in this space. Okay, so we can easily find loops in this space, and it's true for these 4 spaces, and it's true for this space as well, and it's true for this space as well. Okay, so we can easily find loops. Okay, so our next aim is to construct a simply connected covering space of X. Okay, so is it possible to construct a covering space of our space X, which is the wedge sum of S1 and S1, which is simply connected? It's a space where we can't find any loops. Okay, so let's see if it is possible. So starting from this construction, so of course we are going to construct a covering space, and the inverse image of this point X is going to be this point. Okay, so I don't want any loops here, so in other words it should be, so there should be straight edges. Okay, so the inverse image of this A is basically this A, inverse image of this B is this B, and then there are 2 A's and 2 B's. Okay, so in the next step, so remember we don't want any loops in here. So in other words, I don't want to come back to this A or to this B or this A or this B. Okay, so I don't want to come back, so I just want to go on and on. Okay, so at this B there is one edge of B coming in, so I can just define another edge of B going out. Okay, and then at this point, this is going to be the inverse image of this point X. Then I want an edge of A going out and an edge of A coming in. Okay, so this is the inverse image. This is another inverse image. Of course, this is one inverse image of X. This is going to be another inverse image of X. So you can notice that I have drawn this A to be smaller than this A. So we shall see the reason for this. And similarly, at this node, I can do the same procedure. There's one edge of B going out, so I should have one edge of B coming in. So there should be one edge of A going out, one edge of A coming in. Okay, so this is going to be the inverse image of this X, and so the same property holds here. And similarly we can do the procedure over here. So one edge of B going out, one edge of B coming in, one edge of A is already coming in, so we should have one edge of A going out. And same is the case here, one edge of B going out, one edge of B coming in, one edge of A is already going out, so I should have one edge of A coming in. And similarly I can do the same procedure on these nodes, and we can easily see that it's going to be a tree kind of thing where there are 4 edges. There are 4 edges at each and every node, and it's a tree, so there'll be no cycle in it. If there is no cycle in it, then there'll be no closed paths. In other words, there'll be no loops in this space. Okay, so all of these ends will have the same construction again. So I'm just going to do it for one. So one edge of B coming in, so there should be one edge of B going out, one edge of A should go out, and one edge of A should come in. And once again I can do the same procedure over these points. So in general we will get the following diagram. Okay, so it is a simply connected covering space of our space, which is the wedge S1 S1. Okay, so it is simply connected covering space. Okay, so now we are going to answer the following question. If we have a covering space of the space X, then what's the relationship between the fundamental groups of those two spaces? So let's begin. So we have the following theorem, which is called the lifting lemma, and we are going to present this theorem without proof. Okay, so what does this statement of theorem says? So if we have a covering space of a space X, and let this be a path, okay, so any path, okay, and if X naught tilde is in the fiber over X naught, then there exists a unique continuous function In other words, it's going to be another path such that this happens. So let's try to see graphically what happens. So let's consider this space to be X. Now I'm going to sketch the covering space in the following form. Now remember that we assume that our covering space has to be path connected, but I'm going to sketch it in two sheets form so that we realize that it's going to be some number of copies of X. Okay. So if there exists a path, okay, so we are saying that this 0 goes to x naught. Okay, so we have a function, okay, from I, okay, so this closed interval, and the initial point of this is going to be x naught. Okay, so this is x naught. So and there is a path inside the space. Okay, so this is our function f. And if x naught tilde is in the fiber over x naught, so the inverse image, so this is our continuous function p, so the inverse image of x naught will be x1, so we are calling it x naught tilde, and it could be x1 tilde, and there will be one point corresponding to each and every sheet above the space x. Okay, so let's say there are 10 sheets, then there will be 10 inverse images of x naught. Okay, but we are not considering all those points. We just chose one point from one sheet. Okay, so x naught tilde is one point from one of the sheets, which is and this sheet is somehow a copy of x. Okay, so if x naught is in the fiber over x, x naught tilde is in the fiber of x naught, then there exists a unique function. Okay, so from I to this x tilde x naught tilde. Okay, so this 0 goes to x naught tilde. So in other words, so what is this continuous function? Of course it is a path with starting point x naught. So we will get a unique function. So remember, we are emphasizing on this word unique, such that when we apply f tilde first and then we apply p, okay, then it is the same as this f. So if we follow this route and this route, so the answer is same. Okay, so take this path and then apply this projection map, or take directly this path, so it is this. So in other words, we can say that if we have a covering space and if we have a path inside the base space x, then we can lift this path to another path in the covering space such that the initial point x naught tilde is one of the elements in the fiber of x naught. Okay, so it's one of the elements of p inverse x naught. Okay, so remember, this x naught is fixed. Okay, so similarly, if this is x1, we can do the same procedure at x1 by replacing this x naught with x1 tilde, and so this statement will become that if this x1 tilde is in the fiber over x naught, then there exists a unique function, and then replace this x naught tilde with x1 tilde such that this happens. Okay, so this x naught is fixed here. Now let's continue with our quest of finding the relation between the fundamental group of the base space and the covering space. Okay, now we have this covering homotopy lemma. If we have a covering space of the space x, and we have 2 points in x, and we have 2 paths in x from x naught to x1, and x naught tilde is in the fiber of x naught, then we have the following results. If we have a relative homotopy of f and g, then there exists a unique continuous function such that this happens and this holds. Okay, and similarly, if f tilde and g tilde are liftings of f and g, so what does it mean? So according to lifting lemma, we can lift a path inside the covering space. Okay, so these are the liftings according to the lifting lemma, and if f tilde and g tilde are liftings of f and g, with f tilde 0 is equal to x naught tilde is equal to g naught g tilde 0, then f tilde of 1 is equal to g tilde of 1, and they are homotopic. So let's try to understand what this statement is about. So we will go step by step. So let me first state this theorem in a very rough way. Okay, so once again we are going to take this description where where the covering space is basically a collection of sheets on this sheet X. Okay, so this result says that if I have two paths in the space X starting from x0 to x1, so this is f, this is g, okay, and if these two paths are homotopic, so this fact states this fact that these two paths f and g are homotopic. So this is a relative homotopy. So relative homotopy means the initial and the final points of this paths are going to be fixed always. Okay, and then there exists a unique continuous function. So this says that if I take the inverse image of x naught to be x naught tilde, so once again when I am fixing this thing, then I am fixing the sheet on which I am working. So is it going to be the sheet x1 or sheet x2? Okay, because the inverse image of x naught will be in sheet x1 as well as in x2. So there will be another point, let's call it x1 tilde, which is going to be the inverse image. So the inverse image of x naught is going to be x naught tilde, x1 tilde, up to so on. Okay, so basically we fix this sheet, and this result says that the liftings of this f and g, okay, so let's call it f tilde and let's call it g tilde. Okay, so if these are the liftings of f and g, then they will also be homotopic. Okay, so if f and g are homotopic in X, then f tilde and g tilde will also be homotopic, such that their final points are also same. So let's try to first recall ourselves what is relative homotopy. So the relative homotopy is basically a so f0 and f2 f0 and f1 be continuous maps such that f0 restricted to a is equal to f1 restricted to a. So in this case we just need to consider this I, which is closed interval 0 1. So let's restrict ourselves to this, and this a is going to be or I dot, which is basically 0 1. Okay, so it says that these two functions which are functions from x to y, so let me represent one function f0 with this graph and another function with this graph. So of course these graphs will be very complicated in higher dimensions, but I'm just sketching the simplest case where the f1, the graph of f1 is given by this curve, and the graph of f0 is also given by this curve. Okay, so if we have these two continuous functions, then they are homotopic. So relative homotopic. Okay, so relative homotopic means that these endpoints are going to be fixed. So let's see first what is homotopy, and then we will see what is relative homotopy. So homotopy means I will start from this f0 and I will continuously deform this thing into f1. Okay, so there is a continuous change that will take f0 to f1. Okay, so in other words we can say that at time t is equal to 0 we have f0, and at time t is equal to 1 we have f1. Okay, and so the point is for each and every value of the time t, okay, so these values are same for each and every a. So in other words, in this case, or a is equal to 0 and 1, so let's take this small a to be 0. So in other words, this says that for each and every value of t, this 0, okay, so this 0 is going to be the same as f0 of 0 is the same as of 1 of 0. Okay, so this is let's say this is f0 of 0, and this is the same as f1 of 0 as well. Okay, because these paths go like this. Okay, so for each and every t the initial point is the same, and for each and every t the final point is also the same, because these are the points f0 of 1 is equal to f1 of 1, and this condition says that f1 of t, so for each and every t. So for instance, if I take t is equal to 0.5, then I'll get this curve which is going to be x 0.5, and this result says that for each and every value of t, okay, so in particular if I take this to be 0.5, this is going to be a curve, and for x is equal to 0, okay, 0.5, it is going to be this point, okay, and f of 1.5 is going to be this point, okay. So for each and every value of t it is going to be, so for some fixed value of t it is going to be a curve, and the starting and ending point of each and every curve is the same, okay. So let's try to explore this covering homotopy lemma again. So we have the same notations. So I have a base space X, okay, and the covering space which I'm going to draw it as some collection of sheets, okay. So this is my space X, this is the sheet X1, this is the sheet X2. So what is happening in the sheet X? So we have a relative homotopy of f and g. So once again we know that this is f, okay, and this is g, and they are relative homotopic, which means that the initial and final point of each and every intermediate curve is going to be the same, okay. Then there exists a unique continuous function, okay. So what is this function? So we can also review f homotopic to g in the following way, okay. So take I1 cross I1. So we know that I is equal to 0 1, so take I cross I, okay. So if I start from this point, then the image of this line is basically f, and the image of this line is basically g, okay, because basically we are starting from f to g, and the image of any intermediate line, okay, is going to be some intermediate curve between f and g, okay. So in other words, we can say that f is homotopic to g means we should have a continuous function capital F from I cross I, okay, to the space X, such that the following properties holds, which we have already seen in the definition of relative homotopy. And this says that there exists a continuous function f tilde from I cross I to this x1, okay. So we have taken a particular instance of the covering space, particular sheet of the covering space, so such that if this is x0, which sheet? So the sheet containing x0 tilde, okay. And what are the other properties of this f tilde? It says that if I go along f and then go along this p, which is the projection map, then it is the same as this map f. Also f tilde of 0 0, so this is the point 0 0, okay. So the image of 0 0 is basically this point x0, okay, and it says that this point goes to x0, okay. So we can see that this x0 tilde is in the inverse image of this point x0, okay. So let's go to the second part of the this lemma. Now if f and g are liftings of f and g respectively, then f0 0 is equal to g tilde 0, okay, which is equal to x0 tilde, okay. So f of 0 tilde is equal to g of 0 tilde is equal to x0 tilde, and f tilde of 1 is equal to g tilde of 1. So once again I'm going to sketch the diagram. So I have taken two sheets. So on this sheet I have selected this x1. There are some other sheets as well. So this is x. So there are two maps, f and g, which are homotopic to each other. They go like this, and f is homotopic to this. So we have a map from I cross I to the space x, which is the homotopy, relative homotopy of f and g. Then there exists a map, okay, f tilde, which is continuous map, such that this composition is the same as f. Also this point is basically this point is f tilde of 0 0. Okay, now this second part says that if f tilde and g tilde are liftings of f and g, so we have seen that if f and g are liftings, then they should have the same initial point. Okay, so these are the liftings with f tilde of 0 is equal to g tilde of 0. Okay, so this is true, and f tilde of 1 is equal to g tilde of 1. Okay, and this f tilde is basically a homotopy of small f tilde and small g tilde. Okay, so roughly speaking, if there are two paths which are homotopic in the base space, then there will be two paths in one of the sheets. Okay, so there will be two paths which are homotopic to each other in one of the sheets. So how to fix the sheet? So if we give this point x naught tilde. Okay, so if in the inverse image of this x naught there is another point, let's call it x1 tilde, then in this sheet the same thing will happen. So once again, let me say again, if there are two paths in the base space which are homotopic, then there will be two liftings in the covering space which are homotopic. Now let's apply this theorem to the fundamental groups. So before going to the main result, let us call ourselves with this functor pi1. Okay, so this functor is a covariant functor, and so in other words, the only thing that we are going to need over here is if we have a map, a continuous map between two pointed topological spaces x naught and y naught, then this implies, okay, so if this map is P, then there is a map pi1 of P from the fundamental group of x based at x naught. Okay, so set of all homotopic loops based at x naught to the fundamental group of y naught. Okay, so that's the result that we are going to use here, and sometimes we call pi1 of P to be P lower star. Okay, so if we have a covering space, okay, x tilde P to x, then there exists an injection. So remember, this result doesn't guarantee the injection, the one-to-oneness of this map. So it just says that there is going to be a map, there is going to be a homomorphism between this group, and that's it. And it doesn't guarantee the injection or the one-to-oneness of this map. So this result says that this is going to be an injection. Okay, so it will be clear from our previous discussion of covering homotopy lemma and the lifting lemma. So we are going to use, so in particular we are going to use covering homotopy lemma to see that why this result holds. So if we have a map from x tilde, x naught tilde to xx, okay, of course once again, if we have a sheet x and there are two sheets, and in fact there will be many sheets above this thing, so okay, let's call it x1, x2, x3. Okay, so if this is the point x naught and this is the point x naught tilde, then we have a continuous function from this pointed topological space, from this pointed topological space to this pointed topological space. Okay, so if this happens, then, and let's call this map to be P, okay, then we will have a we will have a morphism from pi1 of x tilde, x naught tilde to pi1 x x. We want to show that this morphism is basically an injection, in other words it is one-to-one, then of course we need to show that the kernel of this map is 0. In other words, we want to show that if there is a loop inside the space which goes to 0, then that loop must be 0. So using covering homotopy lemma, we can easily show that. So let's say there exists a loop gamma inside this space. So let's say this is gamma, such that P lower star of gamma is basically 0. So 0 means that it is basically homotopy class of a constant. Okay, so in other words, we are saying that the image of this is going to be constant. So in other words, p lower star gamma is homotopic to constant inside the space X. So let's say this is p lower star of gamma, and this is homotopic to constant. Okay, so we can squeeze this loop to just one point. Okay, so they are homotopic. Now according to covering space lemma, okay, so let's go back. So covering homotopy lemma says that if we have two homotopy maps, F and G, then there will be liftings F tilde and G tilde, which will be homotopic as well, and such that this relationship also happens. Okay, so and let's go back again. This result lifting lemma. So this lifting lemma says that if we have a path inside this space, then there exists a unique. So once again, let me highlight this word unique. So there exists a unique path. Okay, so both of these things represent the following thing. So if I have a path p lower star gamma which is homotopic to constant map, p lower star gamma which is homotopic to constant map, or in other words the identity, then their liftings will also be homotopic. But then what is that unique path such that when we apply p on that map, then we will get p lower star gamma, because we have seen that there will be a unique path such that when we apply p on this, we will get this p lower star gamma. Okay, so let me rephrase this again. There is a path inside the space X, and we want to see that what will be the inverse image of that path under this projection map. Now according to our previous results, there's going to be a unique path such that when we apply p on this thing, we get this loop. So what is that path? When we apply p on this thing, then we will get this loop. Of course that path is gamma. Okay, so when we lift this thing, this p lower star gamma, then we get gamma, and this p lower star gamma is homotopic to constant map. So that's why this gamma will be homotopic to the inverse image of the constant map. Now the inverse image of the constant map, we know that this p lower star is homomorphism, so the inverse image of constant map is constant. So if p lower star gamma is homotopic to constant, then gamma will be homotopic to constant. So in other words, if the image of some non-trivial or some element of this pi1 is 0, then that element must be the identity element. So in other words, this theorem is true, that we will have an injection. Okay, so in other words, we can say that the fundamental group of the covering space, okay, is going to be contained inside pi1 of X. So for the fundamental group of the base. So remember that this covering space is going to be path connected. So if we have a path connected space, then the fundamental group at each and every point is isomorphic. So that's not an issue here. So we can say that the fundamental group of the covering space is isomorphic to subgroup of the fundamental group of the base space. Okay, so so in other words, if we want to study the fundamental group of the base space, then we can study the subgroups of the fundamental group of the base space by considering the fundamental groups of the covering spaces. So the subgroups of the fundamental group of the base space, so they are they correspond to the covering spaces of the base space. Okay, so consider an example over here. So this is a covering space of the circle. So if we have a loop inside this space X, then when we will follow this loop, then basically we will take 3 rounds of this circle. So okay, so let me do this in a slower way. So first thing to notice is the fundamental group of a circle. Okay, we know that the fundamental group of circle is Z, and let's say that it is generated by some element A. Okay, so if it is A, then so this A is basically this loop, this one loop, and if we want to get other elements, then for example A square is just taking two loops of this circle. Okay, and up to so on. Now let's see, let's call this space X tilde. Now the fundamental group of this thing, now it's going to be a circle. Okay, so basically it is a circle, and we have twisted this circle into this form, so this is again going to be integers. So let's say the generator of this is gamma. Now when we now what is the relationship between gamma and A? So when we follow this gamma, and after taking one root, then we have one root in the down circle, and then in the second root, okay, in the second root we have another root along this circle. Okay, and in the third root along this circle, okay, we will have a third root along this thing. Okay, so when we follow this gamma, then we already have three loops in here. So in other words, we can say that P lower star of A is basically, sorry, P lower star of gamma is going to be equal to A cube. Okay, so what is A cube? Taking 3 rounds of this circle, and when we follow this gamma, and then we apply this thing, then we will get A cube, so 3 times along this circle. Okay, so the covering spaces correspond to the subgroups of the fundamental group of the base space. Now the question is, what is the covering space corresponding to the smallest subgroup of the fundamental group of the base space? Okay, so covering spaces corresponds to the subgroups of the fundamental group of the base space. Okay, but the fundamental group of the base space has a subgroup, very special subgroup, which is the identity subgroup. So what is the covering space corresponding to that subgroup identity? Okay, so the answer is universal cover. So what is a universal cover? Universal cover of a space X is a covering space X tilde P such that X tilde is simply connected. Okay, so that's how we define a universal cover of a space. Now we can discuss the universal cover of a circle. So the universal cover of a circle is basically this helix-like construction that we did. Okay, so basically R1 is basically the universal cover of a circle. Okay, so we can easily see that there are no loops in R1. So R1 is simply connected. So this forms basically a universal cover of S1. Now consider the example of a torus. We know that a torus can be obtained by identifying these two opposite sides of a square. Okay, so if I have a loop inside this torus, then this will belong to some path inside this thing. Okay, so now if I don't want any loops, then I want to expand this thing so that it doesn't come back to the same point in this space. So in other words, I want to expand this space like this. Okay, so that when we start from this point, then I can go on, and I will not come back, and the loops inside this space will not give me a loops inside the covering space. Okay, so the covering space is has to be simply connected, and it shouldn't have any loops, non-trivial loops inside this thing. So in other words, we can say that the covering space of this torus is R2, or in general this is basically A2, the affine space of dimension 2. Okay, and similarly we can have two torus. We know that how to obtain a two torus, and we can obtain a two torus in the following way. Take one torus, take another torus, and glue them. Okay, so glue them in the following way. Okay, so cut from here, and then join them, and we will get something like this. Okay, okay, so 1 2 3 4 5 6 7 8, so it's an octagon. So basically this is the sides where we have joined these things. So something like this, and this side goes like this, and like this, and like this, and this side goes to the opposite of this, so basically something like this. And after this point, so basically this point, okay, so this point goes this way, comes in, and goes in the same way, and goes to the opposite way. Okay, so that's how we will obtain a torus. But now if we have this octagon, then using the same idea of covering this plane with this square, now we want to cover this plane with this octagons, but the point is we will not get plane, a fine space, or R2. We will get a hyperbolic plane. Okay, so if we have S2, then the universal cover is S2, and if we have torus or Klein bottle, then the universal cover is R2, or in general we can say A2. And if we have a surface of genus G, then the universal cover is hyperbolic plane. Now in the next lecture we will continue our discussion of the covering spaces. This is the end of the lecture. Thank you very much, and Allah Hafiz.